Well, I'm a little heretic here, I think. I'm of the opinion that quantum mechanics is incomplete. The description of reality of quantum mechanics is incomplete. And the quantum mechanics is essentially a description of our knowledge of the system, of when we restrict the system to belong to a Hilbert space. And that, for me, is clearly an approximation. So I don't think there is much sense in discussing in deep the ontology of quantum mechanics, because it's like describing the ontology of classical thermodynamics. It is classical thermodynamics is complete and perfect, but of course the description of physical reality is incomplete. It doesn't pretend to be anything else, but so I don't see if it makes much sense. But probably it doesn't make much sense to for any theory, not only quantum mechanics. I think that all theories are parts of the study or describe parts of reality. So perhaps taking all of them together, or perhaps in the future we'll have a better theory. I don't know. But regarding what does theoretical and experimental physics can say, well, I think that as far as no new facts, experimental facts appear in a reliable way, there is no much theoretical physics can do. I think that we have to wait until some new experiment provides new data, and then in that case, everything will be more clear for everybody. That's my opinion. Okay? How many hours left? 1 minute. No, well, I think it's all I have to say.
Okay. Sometimes when I talk to physicists or people who aren't philosophers of physics, they get the impression that the reason that there's discussions about the foundations of quantum mechanics is somehow people just don't want to accept what the implications of quantum mechanics are. And sometimes people say, just accept that the world is quantum mechanical. And my response to that is, well, okay, I'll accept that. But what am I accepting when I accept that? What are you telling me when you're telling me that the world is quantum mechanical? And that's the question that motivates me for the ontology of quantum mechanics. And I think the stage we are is we have, there are options on the table. There are different approaches. There's different ways the world could be if it is quantum mechanical. And I don't think that I think we've only begun to scratch the surface of those options. So among various hidden variables theories, we have some explicitly formulated ones like the Bohm theory. I don't think we have a clear sense of what the whole class of possible theories are like that. Same with collapse theories. We have some explicitly formulated collapse theories, but we don't really have a sense what that space is like. What is the role of experimental and theoretical physics? It's got to be our starting point. I'm an empiricist. I don't think we have a priori knowledge about the world. I think physics is our best guide to what there is in the world. I also think, though, we should also pay attention to scientific methodology, because sometimes there's a temptation to think that the role of evidence is some kind of Popperian role, to merely exclude certain things, and then everything else that's left on the table, not excluded, is equally well supported by the evidence, and you have to consult your intuitions or you bring in extra empirical criteria to choose between them. I actually do not think that that's the way scientific inferences work, that evidence can actually favor one theory over the other without logically entailing the negation of one of them. And I think actually, if you think about it, you do think that's how scientific inference works also. Last comment, I do think it makes sense to talk about ontology of a theory even if we are certain that it is not a fundamental theory. There has never, ever been in the history of science anything that has been a candidate for a complete and fundamental theory of the world. But we have been learning a lot about the way the world is, and an awful lot of the ontological conclusions from classical mechanics. thermodynamics, in fact, also, I think, survive the very radical changes that have occurred to physics in the 20th century. How am I doing for time?
I'll be using the time that the others wasted. I won't really. I think it's kind of strange that we talk about the ontology of quantum mechanics, but we're given an ontology in advance and we apply quantum mechanics to it. That is, quantum mechanics is about atoms, electrons, light. These things are all things that we know about independently of quantum mechanics. They're not the ontology of quantum mechanics specifically. So I think the real question about the ontology of quantum mechanics is really about how to interpret quantum states. And that question is really maybe the question of how those states represent the world. What are they representing? They're representing properties of those quantum systems, or systems that can be described in a quantum way, or are they representing knowledge of those systems, or are they representing somehow a bit of both? So I think that's the question. How does a quantum state represent? And how do quantum states that can be superpositions relate to the kinds of states of things that can't be superpositions, so classical states? The role that theoretical and experimental physics plays is, well, I guess we should always try to understand more and more about how the theory is actually used in practice, especially how, and maybe this is something that philosophers of physics should study more, the kind of borderland between classical physics and quantum physics, a semi-classical domain. And I think Elisa Bokolic has a really interesting book about that, which lots of us would probably do well to think more about the detail of the physics of the link between the classical and the quantum in order to understand the ontology of quantum mechanics.
I go? I agree with what has been already said. I mean, I think that there is no, quantum mechanics is incomplete, first of all. And more than that, standard quantum mechanics is so vague and so imprecise that to make ontological consideration on that seems to me quite foolish. It's a good, very good theory about quantum measurements. And there is one ingredient there, which is the wave function or the state, like James was saying. And I also think that the starting point for getting a good understanding of what is going on is reflecting on the role of a wave function. The role of a wave function in standard interpretation, I try to present in my talk, and in Bohmian mechanics as a more clear role, and then in other interpretations too. But you see, you start to understand what is going on if you start from this very strange object, which is the wave function. So my idea is that you should go from there, and then once you have a more precise formulation of quantum theory, you can ask other questions. And another thing that I suggest you should not do is to take observables as a guide to metaphysics or to understand what there is. These are, it's just like operators, all this stuff seems mysterious, but they are just what the doctor ordered to describe in a compact way the result of measurements. And so it's bad to start to dare to construct what there is. It's like to construct, you're a philosopher, I'm not, I'm a physicist. It's like to construct your metaphysics from epistemology, which I think is something bad. And concerning probability, which is often taken as, again, a big innovation, quantum mechanics, my advice, especially to young people, is forget probability. Forget. Concentrate on what there is. Probability comes for free as soon as you analyze the theory. In physics, what really matters are statistical patterns, like in number theory. Now, recently I saw a movie about Ramanujan, and then he was the first that he found a very nice statistical distribution of prime numbers. There quantum number theorists use probability, but of course it's used probability for understanding what are the statistical regularities of prime number. And I think of a physical world in a similar way. A physical theory has to relate with statistical regularity in the world, and not on some number between 0 and 1, which is what we call probability. Of course, this is empirical probabilities. But might say 256. I still have 4 seconds. Okay, you took out 4 seconds out of my
You'll never have that time again.
Well, I agree that we need to look for understanding. But to look for understanding means to look for meaning. And to look for meaning means to look for ontology. Then there are some things I think are important from, at least from the philosophical point of view. First of all, to use Alice's words from yesterday, today we can no more accept armchairs, ontologies, or metaphysics. We need to look to science, and the better science, for instance, quantum mechanics, in order to have a glimpse, at least, of what can be a supposed reality we can postulate that exists. I have a more or less Kantian flavor in saying that I don't believe we will find a definitive theory, a theory would describe reality as it is, if it exists. All we have are models, and better models, as quantum mechanics is perhaps the best one for certain finalities. Then the first thing is that to think about ontology from a perspective of the scientific theories. The second one is to realize that whatever formalism you consider for quantum mechanics, Hilbert space, path integrals, and so on, you can associate different ontologies to the same formalism. Even incompatible and contradictory ontologies can be associated. Then, from the point of view of the theory, we cannot ever know how the world can be, because we can associate different and incompatible ontologies. Then these are things to be considered by the philosophers, perhaps not for the professional physicists, but it has importance for science, for understanding, for comprehension, and for acquiring meaning.
Okay, you're generous. Okay. I was thinking, you know, I like what Olympia said, and I totally agree with that, what she said. But so then I was thinking again about this wonderful quote by Jiva Anandan. I don't know if people knew him, and I hope I can remember. Okay, nature, and I'm just paraphrasing as best I can. Nature is so rich and counterintuitive that we could never have arrived at our theories of nature without the constant guidance provided by experiments, something like that. And my sense is that what's really crucial to remember about discussing the ontology of quantum mechanics is how it was arrived at in the first place. It was arrived at by groping in the dark, by people who really had their own intuitions about how nature is supposed to be, and they really had to give up on that. And that makes a big impression on me, in particular Heisenberg, who had to go away to some island to recover from his allergy attack, and in desperation gave up every single one of his desirable criteria for what a good theory ought to be, and chose to not care about that at all, and did something with the data that made sense and began to predict things accurately. And that, I think, is really important, that the mathematical structure that he created is crazy. And that's what creates all the probabilities that people don't want. It's what creates all the strange non-locality and features that we all find so objectionable. And so my concern, and what I think we should be doing personally, is listening to that formalism. And that's why I think that the many worlds approach has the beginner's mind sort of approach that I think is really important. And in my own work, what I'm doing is I'm looking at more of the mathematical structure that is the dual Hilbert space, and asking, does that refer as well? So in other words, I think that it works so well, this crazy formalism that nobody wanted works so well because it's telling us something about the way nature works. And the more we can take it seriously, and I guess you could call me a structural realist in that sense. I don't really care what it's made of, but the structure is clearly reflecting something powerfully true about nature. So I'm looking at more of that structure and saying, you know, can this give us more clues? So the basic, my basic point here is that I think it's really important to be a little bit loose with ourselves about what we want reality to be like, and think more about what is the theory forcing on us, even if we don't like it, that may just be true.
I always feel so pretentious at these roundtables. I just have a hard time. Yeah, I mean, what does it mean to discuss the ontology of quantum mechanics? It means to look to see what this framework or set of theories is saying about the kinds of objects that exist, and what they're like, what they exist, what kind of causality there is in a world like that, what kind of framework that ontology can exist in, and so on. And the role of theoretical and experimental physics is to provide the starting point and some constraints on what that ontology is going to be. And I'm not like, I think it's refreshing, a lot of the people that debate this aren't like true believers in one particular approach or other, or recognize that there are a lot of different options out there. We don't know, a lot of them are agreeing on all the empirical facts, and so we've got to kind of let a lot of different approaches to ontology kind of flourish and be debated, because at this time we're not going to reach any kind of certainty that one view is correct and the others are wrong. All we can do is kind of look honestly at the physics and see what it's trying to tell us with an open mind. So
I also was intimidated by trying to answer this question without pretension. I wanted to have integrity and to say things I believed in, to still be intellectually cogent, to maybe even conciliate between opposing views. But instead, I think I will be flip and naive and try to stir up conflict. So I've already made this joke that ontology is ideology. A colleague of mine says that all the time, right? And I was raised during the science wars of the 90s, and ontology is ideology. So I don't really believe that, but I do think that ontology is utility for me, right? Especially as a practicing physicist. What is real? I'm willing to explore the thing that the only things that are real are the things that are useful, where useful is obviously a hard concept to define, but I will say that the part that, of course, is most interesting to me is the unreasonable effectiveness of mathematics and the natural sciences. Now, I'm not trying to say that everything is mathematics, right? And in fact, what I'm most interested in is where the limits of mathematics, where we can prove, we know mathematics has limits. I'd like to see where the limits of mathematics, do they tell me something about the limits of what nature, what a framework for nature can give me. As to the second question, when I'm perverting the minds of my students, I give them this hierarchy from data to information to knowledge to judgment. And I say this is a process, right, that we want to sort of carry data. We want to carry the data of the empirical data ideally up to making sound judgments. And maybe even this goes beyond science, but the scientific method, or it's whatever, it's both the fairy tale of the scientific method and the way scientific method is actually done. That's one of the things it's going to do. And theory, right, is this process of deduction, and experiment has this induction. And these are two rational processes that are really useful. But the history of science is full of irrational processes, and the role of intuition in making these steps processes too. And so, again, I am fully supportive of the practice of physics, but I also believe within the practice of physics we have to acknowledge that there is a role outside of theory and experiment for intuition, and for the fact that sometimes the flights of fantasy that we have are smarter than our rational thought can process. There are unprovable truths and undisprovable falsehoods.
Excuse me for being maybe personal. I am a physicist, and I enjoy modest salary, a lot of traveling. But my best benefit, which I get, that I'm not modestly believes that I understand the world as the world at large. I disagree with all these positions that we are not capable. I might be wrong, but I believe that quantum theory is the final word and completely explains everything. Now, today, with quantum, there are many directions of people which really say that it's impossible. We are limited. Only that it's only information. It's only kind of things about. We really cannot understand nature. And I believe, again, for the price of believing that there are some parallel me all over, I have a consistent theory. And of course, to believe in a theory, I need a theory with that there is something is. There is ontology. It's not that things have happened because they happened. They happened because there is something behind it. I think express what's behind is the wave function is the whole ontology. There is nothing else, and it explains everything what I see around. And I have strong feelings that first, it's much better than any other proposal, and second, that it has a real chance to be the final truth. Theoretical physics, yeah, I do all kind of thinking about quantum effects and quantum experiments. I just, again, sorry to say, I think a few days ago, a paper was accepted in Nature Physics in which my proposal of protective measurement has been performed with my guidance. And so essentially, although I don't think that is a very strong argument for ontology, but protective measurement was a story that we can measure wave function of a single particle. We made measurement polarization, expectation value of a polarization operator of a photon. Expectation value, people say statistics, whatever. No, we did it on single photon. So it's kind of the fact that we can measure something on a single particle, the quantum property, not the full wave function, just the expectation value of polarization. I think it's a next step to support my belief that the ontology of the wave function is the right one. Thank you.
Okay, so there's lots of angles that one could take on this, but I'm going to choose one to be deliberately provocative just because I didn't hear anybody else come at it from this angle. With apologies, now I was nice to Hnilo in my talk, and now I'm going to be a little bit provocative. It's interesting that there have been a couple attitudes expressed about the mathematics of quantum mechanics at this conference, which has left out one obvious option. So the two attitudes that we've heard are skepticism about operators, don't be naive about operators, and we've heard the attitude, be naive about the wave function, take the wave function really seriously. It's the thing there, it's there, take it seriously. The theory, it's in the theory. Okay, now I just want to, I'm just, to be a little bit autobiographical and say how I got into this game actually in the first place, is as a graduate student, I was doing logic and philosophy of math, not philosophy of physics. And my advisor, Rob Clifton, he said, hey, I'm working on this problem. Why don't you use your math tools? He said, I'll tell you what it means in physics later. And what the problem is, okay, you have the Cauchy-Specker theorem. Okay, so you can't assign values to all the observables. But what's the best you can do? Can you pick certain subsets of observables and assign them values? So I started out, for better or worse, as a naive realist about operators. However, I use the word operators, not observables, because what Clifton told me is he said, these are quantities. He didn't say observables, he said these are quantities. And the system can't have values for all quantities simultaneously, but what can it have values for? And so, in a sense, for me, always the question has been, in a way, you know, we have to pay a price somewhere. We can't have all these, you know, insofar as we are naive about the operators, we have to make some kind of commitment about which things we think are real. And so I think that's, no one can get around that. You can say, you know, for example, I think, you know, the wave function is real, but really what you're doing is you're saying, I think that certain ones of the operators represent pieces of reality and other ones of them don't. So in particular, if you think of the wave function in configuration space as real, or in, you know, position space, it's the position operator, in a sense, that you're treating as the real quantity. Okay, so in short, that's for me the problem of ontology. And now to come back to a more conciliatory note, I mean, I think that, you know, Bohm solves that. It says we choose position as real. The other quantities, call them quantities still, they're just not possessed all the time. It's usually not possessed by systems. At least what we thought in a naive approach to quantum mechanics as quantities aren't actually quantities of the system.
Well, we finished the 3 minutes, so we can open the discussion. And well, since I took only 1 minute of my time, and exactly I was thinking about saying something very connected what was says now. So I want to stress exactly that, and I would say what I said before, that nobody, or almost nobody, talks about the Cauchy-Specker theorem. And the fact, what I think, is that the most critical part of quantum mechanics is not the wave function, where all the eyes are focusing on, but the fact that there are observables that not commute. If we had no observable, if we had no non-commuting observables, we could understand the wave function in a traditional statistical way. Why we cannot? Because we have a structure where certain observables do not commute. And such a situation is so strange that we cannot assign to all the observables of a system, if we suppose that observables refer to something like properties, or what in the traditional philosophy was determinables, we cannot determinate all the determinables. We cannot assign a case property to all type properties of a system. I mean, a system has many properties that can be assigned to it, but nevertheless, we cannot assign a definite value to all of them. And I think that this is the most basic problem of quantum mechanics, and was not discussed too much. And when somebody begins with observables, with an algebra of observables from the mathematical viewpoint, but I mean from the ontological viewpoint, begins by asking about this feature of quantum mechanics. This is the feature that prevents us to think in quantum mechanics like classical statistical mechanics. So I like to begin by this, but if you don't like, nevertheless, you must take it into account. This is my point. We cannot forget this very basic feature of quantum mechanics.
And to answer, which was, but you see, Olympia, even without going to Bohm, just Landau-Lifshitz, you can explain how operator arise, non-commuting operator, analyzing measurements. Namely, if you just do a unitary evolution of a system with an apparatus and you demand that measurement that this experiment be of a certain kind, you immediately see that the spectral measure of an operator with respect to initial state, you see that the statistic of experiment is given by an operator. So there is nothing mysterious about the arising of operators. It's just a consequence of a dynamical structure, of a linear structure of a theory when you apply to measurement situations. So that's why my emphasis goes to the state. Given this, I'm not at all against using operators. That's of course, Hamiltonian is the basic operator. Actually, I can formulate Bohmian mechanics in Heisenberg representation. I like to do that because you can get certain point much easily than solving Schrödinger equation.
Just to clarify your view, imagine a world. If maybe you say maybe you'll say that we should not do this, but imagine a world that has nothing but a single particle, a quantum mechanical particle, no potential, no measurements because there's no people in this world. Does that particle ever have the property represented by the capital P quantum mechanical operator, or do you think it just cannot have that property? Sorry, cannot? Okay. Yeah, a single particle.
Operators do not represent properties.
Okay, I mean, I just think this is, I mean, that's a controversial point of view to take. I mean, look, I don't expect operators to represent properties. No, I think it's just controversial because I think the naive student, you know, you set them a final exam and you say, describe a quantum mechanical particle alone in a universe. Yeah. And there's two ways a student could respond. They could give a description with Q and P and the free Hamiltonian, or they could say, I'm sorry, in that world there is no big P.
What do you mean big P? Of course, you construct the Hamiltonian using big P. So the P is there because you have a Hamiltonian.
So what is big P, or does it not represent anything?
Is just an operator that you use to construct the Hamiltonian of three parts.
So there's no physical interpretation.
Actually, the major role of P is to be the generator of translation.
But there has no, it's not a reference, has no reference in the ontology. Has nothing. There is nothing in reality.
Reference to ontology.
If you have.
This is standard. Even Bohr would have said that. That's why non-collegiate do such a work of showing that there is no value of operator. Operators are just the tools to describe measurements. This is standard Copenhagen. It's not.
You can accept that. You have to accept that there is another.
You seem not too impressed by the fact that it's easy to explain this non-commutative structure arising. You can give an explanation of that.
Which is the explanation? I mean,
the explanation of providing the statistics for measurements.
But if you have no measurement in that case, that Hans said, what does it mean?
What does it mean? You have a wave function, you have a generator of translation,
why do you say you have a wave
generator of time translations. That's it, that's the theory.
The wave function, if I have no commuting observable, I have no problem with the wave function. This is the point.
Just so, if I understood you correctly before, you said you would not have problem with a wave function when it has classical statistical explanation. It's not explanation. Classical physics, it's one particular line, no statistics whatsoever. This is a complete story. Classical statistics, it's approximation for engineers. It's not anything fundamental. So the complete classical story, it's a trajectory. And then in quantum mechanics, we have this wave function. And from the beginning, when we have a wave function, psi of x, x is not defined, p is not defined, only some particular operator have well defined. Now I have this experiment. I can measure expectation value of p. So this is defined. It's measurable in a single particle. I think this is defined, and it's just property of the wave function. All what we have the wave function. We don't need all these operators. And Cauchy-Specker just help to tell us, forget about them. Don't think about them. From the beginning, we had no reasons to classical physics. Every variable has value. Quantum physics, variables have no values. And then there are additional some theorems that they even cannot have some variables, but they don't have values from the beginning. No, there's no motivation. Properties is a wave function. It is a whole wave function in the shape of me. It's me. Yeah, the shape.
Those are Q values. Those are values of the Q operator. The shape of the wave function.
Shape of the
Q operator.
You can write it this way, other way. Yeah, of course. 3-dimension very important. So this gives us a shape.
I just have a hi. I just have a point of order. This has been such a great conference. So first, I want to thank Olympia and everyone. Fantastic conference. That's really the main thing. This has been really, really excellent. And as I sit here and I really enjoyed all the talks, but sometimes I got this little, painful feeling, like on Star Trek when they, say something wrong and that thing gives you a. And that was when people said, well, we can be naive about this and naive about that. And I'm like, so the word naive, and I understand it's all meant in good spirit and not really as a pejorative, but I do want to urge caution because it, once again, it could be that what we might want to say, well, I don't want to be naive about this, but maybe we should be. On the other hand, what we're calling naive may be the right way of paying attention to the mathematics. So once again, going back to the unwanted mathematical structure with all of the perplexities that it forces on us, we may want to take that seriously. We may want to go. While I was talking to Hnilo about, I understand his point of view, that there's nothing that forces him to say that operators mean that things have that property. And I agree, there's nothing that forces him to do that, and he doesn't have to do it if he doesn't want to. But on the other hand, it's okay to do that. It's a reasonable point of view to say, when the math gives me a diagonal matrix, it's saying something that maybe I ought to pay attention to that's quantitatively and qualitatively different from a non-diagonal matrix. And there's nothing wrong. Just want to put in a plug for, we can avoid making those pejoratives about things being naive or not naive. It's one option, or to maybe you can use a different word, read off the math and go with that. I don't know, whatever you want to call it, but maybe not naive.
I want to go back to the dialectic between Hans and Hnilo, so I thought it was really interesting. And I wanted to make the point, I think, maybe it's relevant, that the first thing that we got of quantum mechanics was the quantum of action in the Planck formula for radiation. And if we looked at, and in our Foundations of Physics course in the physics department, we asked the question, what is a quantum theory? What makes a theory a quantum theory? And one answer that people often say is, well, it's a non-commutative algebra of observables, right? And another answer people often give is, it's the principle of superposition, right? Dirac said quantum mechanics should be called linear mechanics because that's the really crucial thing. But there's a really naive kind of operationalist answer to the question, which is a quantum theory is a theory with H bar in it. Sorry about naive, but what I mean by naive there is it's kind of simplistic in a way. It's kind of an operational answer, right? A quantum theory is a theory with H in it, right? And it's interesting to me that for this free particle in the universe with no other particles, H would be completely irrelevant. because it doesn't figure in the account of position. It only comes in when we think about momentum. So I think that's kind of relevant, but maybe others don't.
There's a lot to say that people have said I want to respond to, but I just want to endorse what Olympia said about the Cauchy-Specker theorem being very important. I didn't mention it, but it's in the back. Because I think one of the things I find interesting is this question, how do we distinguish between classical and quantum theories? And there's lots of different frameworks for doing that. You can compare the Boolean lattices with the lattice of projections on the Hilbert space. They have different structure. You can write classical mechanics in the von Neumann-Koopman formulation, where it's actually a Hilbert space theory. And one thing that keeps coming back when you're talking about the difference between classical and quantum theories is in the quantum theory, abelian versus non-abelian algebras is a major point. And for Hnilo, I wanted to make a plea for taking some of these operators seriously. James alluded to the development of quantum mechanics. Planck, Einstein was the one who really clearly saw that Planck's formula really entailed that energy was being absorbed and emitted in discrete units. One of the big successes of matrix mechanics and Schrödinger wave mechanics is getting the spectrum of the hydrogen atom correct, and those are energy levels. Now, if I'm not supposed to take this H operator seriously as an energy, as a possessed property of an atom whose quantum state is an energy eigenstate, there's big chunks of quantum mechanics that it seems like we're not really taking seriously. Is energy conserved? Do atoms have energy? Do physical systems have energy, and is that conserved, and is it important that it's conserved?
Are there atomic orbitals?
Well, that's another question. Yeah. Is energy a property of something in an energy eigenstate?
Can I? That relation, no, was the one that motivated de Broglie to construct what nowadays we call Boolean mechanics. Namely, the association between a wave property, the frequency, and an energy, and the association, then de Broglie extended to association between velocity and wave number, that means wavelength. So that's of course, that relation is there, and I think is important. It's just the beginning of Boolean mechanics. Boolean mechanics is nothing but the extension to a general wave. This is true for plane waves, to a general wave of this structure. So this structure is there. The frequency of a wave is there. It's real. Nobody says that. But then this manifests in energy, what we call real energy in spectroscopy. In spectroscopy, what you do, you shine light on an atom and then you collect it. Of course, in that you have a nice explanation of why that frequency that appears in the Schrödinger equation describing the atom interacting with matter manifests itself as kinetic energy of the shining particles. So I see a nice story which is relating to what I was saying before, namely that only through interaction, only through measurements, you see the appearance of this property. And here, if you shatter some photons or some particles against the atom, then you see the relation between the difference of frequency and the energy of the outgoing particle. So that in that sense is relevant. And I wanted to add something to what Hans said. Since I have the microphone, I have the power. The fact that in non-relativistic Boolean mechanics, we take one operator and we transform into a beable is accidental. I don't think at all that in general the situation is like that. The beable of a Bohmian-like theory need not to be associated with an operator at all. Actually, this is something that we discussed in the office with Shelley a long time ago, and that Wayne was supposed to write a paper with Rodi exactly to clarify the situation in the relativistic case, in which there are many correct claims about the non-existence of a position operator. And that is not against the extension of relativistic Bohm mechanics. Actually, you can have a formulation of Bohm in which the x, psi of x, that x is not associated to any operator. Did you finish that paper?
We did a lot of work on it, like feverish work in the few weeks following that Lake Placid, and then we all got busy with other things. So it will still be done.
Okay, good.
Yeah.
That was a good clarification on the status of position.
I first want to respond to Ruth and the question of naive. Most people I've noticed are using naive when they're going to say something they think is clever, but they're actually, right, like they're sort of self-referring, self-deprecating to actually, right? So let me say something naive, which is, so when I think about, it was your question about energy, right? And this question about whether that's something that means something. So again, if I come back to this idea of what is useful, then right, if I have some quantity that I can say all observers agree on because it's an invariant under all reference frames, or some subset of observers agree on, right? So to me, it's just so hard. It's so hard not to grant that some sort of ontological nature if I can say everyone who makes, and so obviously position's not going to be like that, right? Because we don't agree on that. That is clearly not that. But in relativistic mechanics, right, it's S squared, and in non-relativistic it's M, and there are things that everyone would agree on. What? Internal energy, right? I mean, in Galilean, there's the three invariants, right? I mean, yeah, so we can go through these things. It's so hard for me to give up how useful these are, how naturally they emerge from the mathematical structure, and then this universality of observation that comes from it. So I need that to come out of whatever anybody else tells me, right? I need that to emerge from your ontologies if I'm going to take them seriously.
May I just remark about importance of energy?
Of course, we cheer. We are very happy about it.
Yeah.
They're basic for so I didn't get your point.
Just about energy. I think many physicists, some departments, the only physical problem is to find the spectrum of energy. Because after you found the spectrum of energy, multiply, and then you know the whole evolution, you know what's happening. It's a technicality. Now, this technicality, useful technicality, so then people ask energy. Does energy has, is it real, whatever? No, it just allows us to solve, to solve the problem. And then mathematics. Mathematics is a kind of great thing, and I think it's a miracle that we can explain everything, almost everything we see around with physics, which use simple mathematics. I'm not sure that one have to look on all mathematics and all structures which we can find with algebras and whatever, and say that they must have some physical meaning. But it looks like if there are elegant things, it doesn't mean necessarily that they represent any connection to our nature.
Sometimes they do.
Sometimes they do.
I want to raise another thing that probably no one will pick up, but when I was studying quantum mechanics, my teacher, Tony Sudbury, wrote on the board one day, physics equals IH bar times mathematics. And then what the lesson was about was the derivation of the commutation relations of angular momentum. And I just wondered what the Bohmian, I mean, this is not, it's not just a genuine question, right? Because if you take the operator kind of way of thinking seriously, then you have this really neat story, like translations in space commute. And that's why components of linear momentum of a particle commute. But rotations in space do not commute. And that's why the angular momentum of components in different orthogonal directions don't commute for a single particle. Now, what's the story about that? Is that just some, I mean, that comes out of statistics or something, right? I mean, it seems like it's something about the structure of rotations and angular momentum that just makes it true for a single particle that those components don't commute. It's got nothing to do with statistics, but it sounds like difficult to reconstruct anything like that on the Bohm picture.
No. I understand your question. Operator appears in different ways. They are related to measurements, and they are related to the basic symmetry group of a theory. Your question about angular momentum is answered by group theory. Namely, these are the infinitesimal generator of rotations, and they don't commute. Period. It's nothing to do with measurements. It's a group theoretical fact. And Bohmians use even creation annihilation operators, because these are the best way to construct a an Hamiltonian quantum field theory. You even use quantum fields. So we use all kinds of operators. And a question for everybody, not just for Bohmian, is the relationship between operator associated to symmetry groups and operators as a tool to provide the statistic of measurements. But in quantum mechanics, since it's a linear theory, it's not surprising that linear operators are playing a relevant role. And Lev just said, take the Hamiltonian. The Hamiltonian is essential because when you diagonalize, you solve the equation of motion. And when you work with angular momentum, you have immediately a classification of all quantum numbers, like in the hydrogen atom, because this is just coming from group theoretical consideration. Bohmian, in these things, they do the same as everybody else. The only claim about the non-essentialness of operator is operator as observables. Otherwise, operators as generator of symmetry, operators as the Hamiltonian, and so on, they are essential to quantum mechanics. No Bohmian will say they are not important. But one thing is to be important, another thing is what is real, and this I agree completely with Lev. In a Bohmian case, I had the position, but then the wave function is real. That something is important doesn't mean that it's real. That's the point of Lev, it is also my point. It's really important in the formulation of a theory of the operator structure. With creation and annihilation, it's difficult to build up a quantum field theory.
When you measure something. What do you measure? A body, an individual, a property, an event? What are you measuring? What is something that you say that has a value? I mean,
very good question. Very good question. Now, my answer is not original. It's the answer of Bell in a beautiful paper against measurements. Measurement is a bad word. There is no such a thing as measurement. No. No, I talk about measure. I talk about measure to be understood. The good word is experiment. And second thing, Bohr never talked of measuring property. Bohr taught us that the result of a measurement, he was using the name measurement, but it's better to use the word experiment. The outcome of an experiment is the result, this outcome is due to the interaction between the system and apparatus. And there is no pre-existing property. And that's what you see at work in Bohmian mechanics. There is no pre-existing property. It's very close to the Bohr idea.
I'm not saying that the property is pre-existing. I'm saying that when you make an experiment and you write a number on a paper, what that number represents. This is my question.
That number represents take a Stern-Gerlach experiment. A Stern-Gerlach experiment, you should shoot a neutral, let's say an electron, even though an electron is not good, you should take a neutral particle. But okay, take an electron to a Stern-Gerlach. Then the outcome of experiment is the spin goes up or the spin goes down. That's the outcome of experiment.
So you write here to put
Plus or minus, yes, according to whether the particle went up or went down.
That there is a not property, it's something.
No. That something is the result of putting an inhomogeneous magnetic field. If you don't put the inhomogeneous magnetic field, you don't have going up and going down.
More basic. I'm asking.
There is no property.
More basic. When I say, I ask you, what is the color of this thing? You say something, and that something seems to be a property of something.
Yeah, sure. Classical physics is like that. In quantum physics, there is nothing like that. But this is what standard Copenhagen taught us. No, but in Bohm you can really see why is any experiment is due to the interaction of a system and an apparatus. And there is no such, you like this no-go theorem. This no-go theorem says that you cannot interpret operators as providing properties. And it is in agreement with experimental practice. When you do an experiment, you interact with the system, and the outcome is not revealing a pre-existing property. Like the white. It's not doing that.
But there is a screen that has a property.
Sure, you measure spin up or spin down.
Wave function.
I don't see the wave function. I see a spot on the screen. What is this?
This is correspond to a wave function.
No, that's a bit too fast. I mean, it corresponds to the fact that a wave packet is splitted, and then there is a certain chance of going up and a certain chance of revealing down. But that's all there is. There is nothing else behind this. Is a property of evolution of wave function, Lev would say, and I would agree with that.
So when a student when they're in the lab and the person says, I just measured the momentum recoil of such and such, you think, they're really wrong. There is no momentum. It's revisionary, totally revisionary.
There is a property of the wave function.
Of having a certain momentum value.
Property of the wave function. If the wave function has e to the I kx, it has momentum k or h. That's all. Describe particular property of the wave function.
Okay, so
there is no momentum. There is no meaningful momentum. There is only wave function. And if it's a particular shape, then
there's a meaningful momentum.
Then there is an eigenvalue, eigen whatever link.
Yeah, there is a property. Okay, there is something that is a property. So even if we accept that the wave function is there is something else.
No.
What is property? You said there is a property. Come on.
You speak about shape.
Property. You said this is a property of the wave function. So there is a wave function, and the wave function have properties.
The wave function is a complicated. It's a function. And the function, you can see if it's even
has properties.
If it's bounded or unbounded. If it's what is the
Okay.
Fourier transform?
But what do you? Why people?
Any question and all these questions. These are properties.
Okay, but ontology doesn't mean that you only have to individuate individuals or things. You have to give things and the properties of things and how things behave and how things are related with other things. So,
the wave function, I give you everything. It includes everything. You can add, and it's helpful to add these properties. They help to build machine and whatever, but they are already inside the information in the wave function.
The property is inside the wave function.
Of course, there is a property of me. But my weight, my color, whatever, it's my property. But just give me complete description. It's fine.
No, just to make it, now I differentiate from Lev, even though I agree mostly with him. But he has a many word in understanding. My word is single word. In a single word, I need the position of particles. And most of the results are determined by position of particles. But this doesn't mean that there is a property in the sense of an operator or whatever, but particles behave in a certain way and in an experiment as a result of an interaction with something else. And that is what you measure in Bohm. In many words, you do something, the interpretation is slightly different. So we agree until a certain point and then we split.
I just want to pick up on the real is useful and it might be important, but it's not real. And I'm kind to think that if something is important and useful, then it's real. And I'm thinking also that I find really what Lev says really confusing, because whenever there's a wave function, it's attributed to something, right? It's the wave function of an electron or the wave function of a buckyball, right? You can't say there's only wave function because a buckyball has got all this structure, and if it's got a wave function, the wave function is predicated of that thing. And then going back to the useful, important thing, I kind of think that we have quantum field theory, and quantum field theory doesn't start with wave functions, and it doesn't start with positions. It starts with fields, and then you quantize by and what it means to quantize is to get an algebra of operators that represent the field.
Or you define the functional. Field theory with functional is complete description. It's not. It's more. It's richer. It's not just you cannot have. If you have more particles, it's a very functional. And people, this is a very legitimate description of the whole world. If you want to go to field theory, well, you want to have creation, annihilation, everything. So it's not what wave function, it's wave functional. Sometimes you have some Grassmann, whatever, some mathematical difficulties, but the type of thing, it's the same story. No algebra. No algebra. We have this wave functional and its evolution in time. I don't want to know. I don't need operators might help me, and algebras might help me, but they not have no any kind of. They're not. Wave function is what is algebra, but algebra. You from the beginning, you know, you cannot rely your algebra. Your variables do not all of them have values. Now you have to play some, have some. No. But why do you know that? My wave function has values.
Let me. Now, you speak about shape, right? And you speak about an interaction between something and your measuring apparatus. So when you speak about shape and about interaction, you are being loosey. Because this shape of the wave function is a very definite mathematical object. The shape is not like a shape of a wave in water. It's a density operator acting on a Hilbert space, a trace class operator. Yes, it's a functional. You mentioned it. And it has a lot of properties. And wait. Let me speak. Can I speak? May I speak or not? Maybe if you want. So the thing is, it has very definite properties, and these properties vary from system to system. So I find it a little bit schizophrenic to deny that this interaction is not related to properties of a definite system. For example, in the Stern-Gerlach apparatus, there's something interacting with the magnetic field. There's something there. Maybe you want to deny it and say that this does not exist. And it's a nice ontological possibility. It's okay. But you must acknowledge that there's some people that want to believe in the formalism. That's my...
No, sorry. I'm a theoretical physicist that has done for all his life mathematics and mathematical physics. So you cannot say that I'm slopping what I'm saying, okay? Because I try to speak in a way not technical, not to confuse people. But I know very well what I'm talking about. And when I say that has to do interaction, I can give you a trivial example so you can follow. In which way, for instance, momentum arises in Bohmian mechanics. Is using an old idea of Heisenberg, namely measuring the time of flight. What you do in a measure of momentum, that's Heisenberg suggested that in 1927, you look at how the particle started here with a given wave function, and then you measure the position after a large time t. Then you take m times x of t minus x naught divided by capital T, and that is momentum, okay? For simplicity, let me put x of 0 equal to 0, put the coordinates there. Mathematical theorem. The random variable x of t over t times m is distributing according to the Fourier transform of initial psi. That's a mathematical theorem. And that is the simplest way in which you can measure momentum and to see how momentum can appear as a probability distribution of a random variable generated with x. And many other situations are reduced to this way, in this way. So there is a clean way of understanding in which sense an interaction. Why I say an interaction? Because here you want to say measure the momentum of a particle which is bound in an atom. That was the suggestion of Heisenberg. Then what you do, you ionize the atom and you let the electron go freely. And this going freely produce dynamically the Fourier transform. But this is a mathematical theory. That means all this interaction can be treated in a mathematical way. In our paper, we prove, for instance, that under very general assumption, the unitary evolution of an Abomian situation, you get as a probability distribution a POV measure. So I'm just referring to serious and concrete mathematics, difficult theorems, not trivial things. So I don't accept the thing that I'm slopping what I'm saying. I'm trying simply to say how you can implement an idea. I mean, what physicists really do, the experiments are of this kind, momentum. Who cares? You have to do something on the particle to measure momentum. And that is a very simple way, it was suggested by Heisenberg. And then so in this way you get in a theory in which momentum is not primitive, you have a good understanding of what momentum means.
But you don't know that problem because you believe that there is a property there.
Sure, but this computation can be done. Heisenberg did it in Heisenberg representation. So that means it's not something peculiar to Bohm to think in these terms. Everybody that grew up in quantum mechanics understood that the outcome of a measurement is the joint effect of interaction of a system with an apparatus. It's just a question of making mathematically precise this, and Bohm allow you to make a little bit more steps than in the usual framework. But what I just described, for instance, you find a similar explanation for people using Feynman-Patty integral. So I want to say this is not something strange of Bohmians or whatever. The idea of thinking of a result of measurement, of experiment, I should say, in this way, in a very concrete way, interaction of something with something else, that's what is quantum mechanics about.
So let me wind my way back to this discussion by first starting out, right, that an intellectual issue that I think is sort of socially important, right? We have all these people who are collecting data, right? Big data on the thing, and they're using big data to predict voter measurements, and they're using big data to sell us things in the end, and they're using big data to rate our credit and big data to make these kinds of judgments, right? And so, and when you talk to some of the big data people, what they say is, right, is the data doesn't lie, right? And that this emerges from the data itself. And of course, then we go and we talk about maybe computation, and right, and you can always, if you picture a Turing machine, right, you have this long string of zeros and ones, and then you have the little Turing machine that's running up along it, right, and you can sort of try to think about, okay, well, what's the output of this long string, right? Well, and you could say, well, you could try to think like, okay, well, so the more complicated the output, the longer the string. But of course, no matter how complicated the output is, you could just have a Turing machine that was so complicated in itself that if you just give it the answer, you give it the number 1, it produces the right output, and 0, it produces nonsense, right? I mean, in other words, there's a trade-off between the input and the interpreter. Or the example I always give my students, right, is the first time we teach you electromagnetism, we give you the integral form of the equation, because you can't handle the differential form of the equation, which looks much simpler and is much nicer. And then you get a little bit more sophisticated, and we give you the two equations in terms of the, we give you two equations in terms of f, and then we go even to the potential, and then we just have one equation with D'Alembert. But what we've done, right, is we've transferred the difficulty from the the first representation. We had much more of it laying out there, and we've transferred the complexity to the interpretive structure, right? And so what I feel like when I hear this discussion, this was all I'm trying to get to, right, is so when we talk about the wave function, right, my instinct is that the wave function is the data, right? And so then you can say, can I get an interpretation, or can I get measurements, can I get observables, can I get everything I want to know out of the wave function from just the wave function itself? Or do I have to have some sort of way to decode the wave function into the empirical world? And I have the feeling you can't do it just from the data. You have to have some other structure. And so my ontology has to have something besides the data. It has to have a way of generating the interpretive structure. For me, that's math, right? And so my ontology has to you're saying, of course, you use math, and you know that, right? But I'm saying my ontology has to explain why there is math, what the math is, and why the math is effective, or at least it has to assume that as a thing.
Exactly. Just the operators, whatever, very helpful, and I use them. They just don't have values. Everything is just, the ontology is just the data, which you said. Then it has structure, and there is a mathematical structure, very helpful. If I want to know evolution of my wave function of my data, I will use all these mathematical apparatus, and sometimes I will study algebra. But algebra of things which do not have values. The values is just the data. The data was, the wave function is the only ontology. I don't need any other ontology. I know that Hnilo wants one word, and then he make it economically with one more ontology. But I don't need any more ontology.
I think the point is a little bit different. I mean, the point is, given a wave function, which is a mathematical object. Wait. Yeah, I mean, I don't show me a wave function.
You as a wave function.
No. I mean, please don't tell my children. I mean, they think that I'm a human being. No, okay. So listen, I think the point here. I mean, I'm just trying to interpret. I'm trying to interpret the data I was given here.
Yeah.
And I think it's a very interesting point, and I don't think necessarily undermines your position. I just think it's a very interesting point. Is if you hand me a mathematical wave function, so in other words, you've written down on a sheet of paper something, and then you say, that represents reality. I don't know yet what to say. I need to know how it represents reality, right? So I need to know, for example, how to interpret. So I see in my description let's say at pi, the value is 3 plus 2i. And I think, what does that mean? That's just a number. Pi, 3 plus 2i, what does that mean? I go, oh, that's here in space. I take the modulus of that. That means, it kind of goes that high there as a shape. But now I've used a position operator to talk about. So I've decoded the mathematical information of the wave function.
Applied this to wave function. And found some of its properties.
Yes. So in other words, but notice then you have two things leading to physical meaning: wave function, coordinatization with operators.
Space is given. I don't like it.
We will run us from the place because we have to leave the place. So since Ruth is so nice, I propose that she makes the last.
I'm so nice. Oh, that's so funny. A lot of people would not go along with that. But yeah, I just want to remark that again, when we're talking a lot about the wave function, what we really mean, I hope, is a state vector. We don't mean to coordinatize it necessarily. So, and then the question is, does that refer to something? And clearly that's a big problem because it's got its complex multidimensional character, and so obviously whatever it refers to, has to be weird. And in my interpretation, I do deal with that issue head on. So I don't want to make an advertisement and all, be tacky, but there are people doing that, addressing that very problem about, you know, if it does refer to something, if it's not just a mathematical object, what is it referring to physically? So yeah, important question.
Just to finish, because people has to close here and clean. Just to close the meeting, I want to, of course, say thank you, all of you. I hope that you enjoyed the meeting. I think that it was not boring, at least. And well, I want to thank all the students and collaborators because they are absolutely great. Well, and we are here because, of course, University of Buenos Aires and CONICET pays our salaries, but I want to say that if we had not the grant from the Templeton Foundation, we would not be here either. So thank you very much to the foundation, and I hope that they will be satisfied with our work, and we can continue to do this kind of work and meetings. So thank you, all of you, and well, and tomorrow, just enjoy. I wait you at 9:30 at the door of the hotel. There will be a bus for us, and just enjoy life. Thank you.
Let's thank Olympia for that.